Hi everyone. Today I'll be giving a overview talk of the geometric realizations of Hecke algebras due to Bezrukavnikov. And I'm going to do this seated down. I cannot walk right now. Okay, so I'll begin with giving an introduction to how Hecke algebras arise in number theory. So this has to do with p-adic groups, representation of p-adic groups. And we can work over any local field, but just to ground ourselves first, we'll just work with the p-adic numbers. And then I'll let ZP be the ring of integers. And K will be the residue field. So it'll be the finite field FP. And now on the group side, we're going to work with a split reductive linear algebraic group over the finite field. So linear means closed subgroup of GLN, and P will be a Borel. And now the Iwo-Hori, denoted by I, will be the pre-image of the Borel under the evaluation map. In other words, you take the group with p-adic integer coefficients and you do mod p. So Iwo-Hori is the pre-image of the Borel. Now let's go straight into the definition of the Iwo-Hori Hecke algebra. So this will consist of compactly supported functions on this double quotient space. So the I mod p I consists of compactly supported functions on the p-adic group. They're complex valued. And it's bi-equivariant with respect to Iwo-Hori. Now, this comes with a convolution product. So a priori, it's not like just easy. It's not commutative. So we equip with the convolution product. This, to remind you, it's given by this integrating f1 of y times f2 of y inverse x. So this p-adic group is a locally compact group, so it has a Haar measure, and we integrate with respect to this Haar measure. this. Now, abstractly, this definition doesn't really shed light at all to what it looks like. So what we can do is look at the Bruchal decomposition of this double quotient space and deduce that the Hecke algebra has a basis or an algebraic basis indexed by elements of the affine vowel group. So here W will be the finite vowel group and Q is the co-root lattice of G. And to be safe, I'm going to assume that G is simply connected to avoid any ambiguity between co-root and co-weight, so that then, in particular, the affine vowel group is a Coxeter group. So it's generated by reflection satisfying braid relations. Now there's a completely algebraic way to define the Hecke algebra due to Bernstein. And this general construction now is sort of defined over the integers, and it applies for any Coxeter group. So let WS be a Coxeter group, then Hecke algebra associated to W, so it's denoted by boldface H, is generated, or it has a basis over the integers with Q plus minus 1 attached formally. So Q is thought of as a formal parameter. It's given by these symbols T sub W, where W ranges through all elements of the vowel group. And there's only two relations. First is this Q deformed quadratic relation. So Ts plus 1 times Ts minus Q is 0 for all simple reflections. So yeah, I maybe implicitly, right, so S is the set of simple reflections. And second relation is that you can multiply generators when the lengths add. So Ty times Tw is Ty times W if the length of Y plus the length of W is the length of Y times W. And sort of I mentioned this twice, but just to write it down, thus this boldface H, this affine Hecke algebra, or this Hecke algebra, is a Q deformation of the group algebra of W. Notice I did not assume W is finite or affine. So this construction allows for affine vowel groups. And by Q deformation, I mean when Q is set to 1, you recover the group algebra. Okay. Any questions? There's a PPW basis. Given by monomials in X times finite vowel group. So here lambda is in Q check, the co-root lattice, and W is in W finite. So this is like a PPW basis. And we will use this feature many times throughout. And then in this basis, we can also write down the generators and relations. So with this presentation, the algebra generated by just the finite vowel group elements is equal to the finite Hecke algebra. And the algebra generated by all the X is commutative. It's just a polynomial algebra or Laurent polynomial algebra. So we can write it once we pick a basis. It looks like x1 the xn plus minus 1. So you should think of these as functions on the torus, multiplicative torus. And this q plus minus 1 means like it has also some additional C star dilation action, which sort of keeps track of the degree. Then there's only two relations how to move the t's across the x's. First is if the roots are sufficiently far, they commute. And secondly, when the pairing between the root and the co-root is 1, then the generators Q commute. Oh. I'll say it that way. So these are all the generators and relations using this PPW basis. Now, here's a fact, which is due to Bernstein. It's purely algebraic. The two notions of Hecke algebras we have defined are the same. And I need to complexify the algebraic definition because it was defined over the integers. And just to be very like pedantic, I'm going to write down sort of the Hecke algebra associated to a dual root system because notice in this Bruchal decomposition, the elements, the bases are indexed by elements of this dual root system of G. So here we sort of see our first instance of this like Langlands duality philosophy in the sense that if we want to study representations of the p-adic group in the representation of this algebra, it's related to representations of this affine Hecke algebra for the dual root system. And it is very simple to see how these algebras are related. So these generators T sub W, where W is any element of the affine vowel group, it just gets mapped to the delta function on the Bruchal cell times some constant, maybe some power of Q. I'll just put like some, let's see, lambda. This is non-zero constant. This is the and then to sort of finish this introduction, the main like local Langlands conjecture in super rough form relates irreducible representations of the Hecke algebra to certain Galois representations. So I will formulate it in the following way. So this is like local Langlands conjecture for finite fields. So we start with, on the left-hand side of these irreducible p-adic group representations. With I fixed vector. Namely, this is some representation on this algebra up here. And then the fact, so this, there's no theorem here. This is just the same thing as reducible Hecke algebra. Modules. And I mean the complexified version of this with no I fixed vectors. And then sort of, here's the mysterious dotted arrow where I'll be very, very vague and just say that this should be related to certain tame reps of the Galois group. Yeah, and then sort of if the first fact, you start with the representation of the p-adic group. It has I fixed vector, so then you can take its I fixed points. And then it turns out, I mean, just directly follows that from this isomorphism, this vector space is also a Hecke action, Hecke module. So the classification, yeah, so it's very important to classify the irreducible modules for this Hecke algebra over here. And this was done by Kazhdan and Lusztig. So classification of modules for this affine Hecke algebra done by Kazhdan and Lusztig, and also sort of by Ginsberg. And so the first step in this classification was to pass to the geometry, to the K-theory. And this is what we will sort of focus on for the rest of the first half. K-theory, Steinberg. Any questions? Okay, so here's the setting we're working with. X will be some quasi-projective variety with a equipped G action. So G is same as before, split, reductive, linear, simply connected. And now we consider this coherent category, coherent sheaves, which are G equivariant. So they're just locally free. And then the K theory is just the Grothendieck group of this category. So I'll suppress like writing K of Koch Gx and just write Kg of x. And just very quick reminder, this is just the group algebra of the isomorphism classes of the simple objects, modulo the relation that all short exact sequences split. Now, let's do some easy examples. So the first example is the K theory of the point. So coherent sheaves over a point are just vector spaces, and we require a G action. So these are just representations of G. And this is just denoted by R of G, the representation ring. And since G is reductive, this is the same thing as just class functions on G. In the case of finite groups, this is very classical. The next example is sort of the K theory of C star, well, or the K theory of any affine space. It's the same thing as for a point. So let me just write down a few things. And this will be sort of, when you impose the C star equivariance, it will, so C star acts by dilation, and the effect on K theory is it attaches this formal parameter Q plus minus 1. Sort of maybe a less trivial example, but one which will be used all the time. So H now will be a closed subgroup of G. The K theory of this will sort of looking at sheaves on G mod H, which are equivariant with respect to the G action, like the two G's cancel out. So it will be just K theory of point mod H, or in other words, the H equivariant of point. For instance, the K theory of G mod B will just be R of B. Now, the one that we will use a lot is now the K theory of Springer. So let and tilde denote the cotangent bundle of G mod B. And let's now compute. So we can rewrite T star G mod B as G cross the Lie algebra of B perp, namely N. Over B. And then we can use fact 3 to sort of cancel the two G contributions. So this will now be the K theory of fractor N mod B. But the K theory for any affine space is the same as for a point. Now this is just R of B, but R of B, so these are just looking at representations of B. They're determined by the highest weight. So say R of t. Representation ring of the torus. And this is just like the same as the polynomial algebra, the Laurent polynomial algebra. So as defined, the K theory only is equipped with a additive group structure. In certain cases, we can equip it with a convolution.
Second from last line.
Sorry?
Second from the last line.
Yeah. It's the same thing. Yeah, so the passage from this equality to this equality is replacing vector space by point, but then the representation ring of the Borel is the same as the representation ring of the torus. For the same reason, like the Borel is torus times unipotent, but like the unipotent has no contribution. Products of okay. Any other question? So let's now discuss the convolution product for very special G varieties. Yeah, so not all varieties X have a product. But it turns out for varieties of the form like that are symmetric, Z cross Z, or even more generally, Z cross Z hybrid over Y, there exists a natural convolution product. Which is given in the usual way. I'll just remind you. So we take two coherent sheaves over X. Then we pull them back along the projection. And then we push them forward along the projection. So here, the PIJs are maps from 3 copies of Z to 2 copies of Z. And the sort of reason why the convolution lands in the correct space is the like intersection of X with itself is X, or in other words, like it's this exercise in set theory, the image of the pullback of X along both projections is X. So yeah, obviously for us, X will be the Steinberg, which is defined in this way. There's also another big class of varieties which there exists a natural convolution, and those are for smooth varieties. So this is like the spring resolution, like the cotangent bundle of G mod B. F tensor product, so F tensor G, which agrees with the convolution product. Here, delta is just a diagonal inclusion. The reason why we need smooth here is because in general, tensor product doesn't need not preserve coherence, but it does for smooth. Okay, so I'm going to now use the standard notation for Steinberg, which is given by a capital Z. This will be defined by this fiber product of Springer with Springer over the nilpotent cone. And just as a set, this consists of triples. Side. So X is an element of the Lie algebra, and then B and B prime are Borels, which contain X. And just as an aside, in the second half, we're going to work everything derivatively. This is not the correct object to look. In that case, it would be the fiber product, it will be over G, not N. Okay, so here's the main theorem. The K-theory of Steinberg is the Hecke algebra. There is, and moreover, it's an isomorphism of algebras. Yeah, so this holds for the same restrictions on G as before. And so just as an aside, by specializing to Q equals 1, so specializing in K theory gets rid of the C star action, and we just get isomorphism at the G equivariant K theory of Steinberg is the group algebra of affine group. And if we specialize to P, the time P, get the Iwahori. So this isomorphism really is like, it's a it generalizes. I mean, it's a way to realize the Hecke algebra where Q is treated as a formal parameter, and then you can specialize to sort of recover the initial fact we saw before. So the original plan was to discuss this for SL2, but I decided it's way too technical, so I wrote notes, which I'll post. Let me just discuss a proof sketch in general. It's quite a standard approach, like which we see with all sorts of Hecke algebras and their like relatives, like Dahas or Geometrization algebras. So section proof strategy of the main theorem. So there's two main steps. First is to construct a map of algebras, and this will be done by generators and relations. So construct map data from Hecke to K-theory. And the way this will be done, so there's an easy part and a hard part. So the easy part is the polynomial part, x to the lambda. So lambda is it's a co-root. This will get mapped to, well, let me draw this little figure. The Springer resolution is the cotangent bundle G mod B. This maps down to G mod B. So we can take a line bundle O of lambda on G mod B and pull it back. And then we can embed Springer into Steinberg diagonally. So then we push forward. Now this is a coherent sheaf on the Steinberg. Let me say this here. Now for the generators of the finite Hecke algebra, it's a little bit harder to write down. I'll write down a formula and then just say it works. So for each, so G mod B has decomposition by Broussard-Cells again, like the B equivariant orbits. And then we can now sort of double this and instead look at the B orbits inside G mod B cross G mod B. Take the cell corresponding to the simple reflection S. And then we can take the co-normal now this is some Lagrangian. And what we, so another fact about Steinberg, the Steinberg can be written, so all of the irreducible components of the Steinberg are of the form co-normal to G mod B cross G mod B along each Broussard-Cell. So this is like some irreducible. Okay, so what we do is we look at the sheaf of relative differentials down here. We pull it back along this projection. And this defines now a class of Steinberg. So this conormal is a component of Steinberg, so it's a class of Steinberg. What we do is multiply this by Q, and we add the trivial. Okay. Everyone can hear okay on Zoom? Okay, perfect. Thank you. Yes, somehow I disconnected. So I am scrolling, but it's not showing. Well, sorry about that. Wait.
Chris.
Let me try again. Yeah, okay, so this is the map. And it's impossible to show that it's a map of algebras directly. Like the key point for the SL2 computation is that you can do this directly, but in general, it's very hard. But there's a trick to bypass showing it's a relation, and that is by sort of finding a faithful representation of both sides, showing that this representation is the same, and that each generator acts the same way. So the idea is to show both algebras admit the same faithful polynomial representation. So sometimes this is called anti-spherical. Maybe I can try to just. I mean, okay, I'll try it again and then see what happens. At the break, I'll decide whether I can speak on one foot. There's like a non-zero chance I can. Right, so this faithful representation is called polynomial rep, and let me explain why. So let E be this symmetrizing idempotent. And let HE be the induced left H module. Now there's a fact that this is so this epsilon is the character of the finite Hecke algebra given by sending the T generator to some power of Q. Now, why this is important is remember in the PBW basis, H was like the tensor product of some polynomial part X and some finite part T. So what this is saying is you sort of kill off all the T's and all that's remaining are the X's. So that's why this HE is called a polynomial representation. Some people call it anti-spherical. I don't know why. But this works. So thus, and yeah, sort of, I'll say fact, this map is effective. It's a faithful representation. And here's sort of the diagram which everything fits together. I'll put this sort of in dotted. We don't know it's an algebra map, we just have it's a vector space map. We've constructed here a faithful representation. And now we need to complete it on the bottom. And you want to take a guess what representation we take? Should be K theory of something. It's K-theory of Springer. Write down. So recall that computed the K-theory. This was just a representation ring of the torus. The torus was just these X generators. So and we also show that this polynomial algebra in X is just this HE. So we can write down HE as left modules for the Hecke algebra. This in particular implies that the endomorphism algebras are isomorphic as algebras. And now, how does the K-theory of Steinberg act on Springer? Well, that's just by convolution. So this has an action by convolution. And here, the key property is that if you intersect Steinberg with Springer, you get Springer. Namely, like n times n intersect with n is n. And yes, this is also a faithful representation. And this diagram commutes. So this directly implies theta is an algebra Hom. And by the way, we may one other way that this representation on the left appears is sometimes called like de Bezrukavnikov operators. So the x's act by multiplication by x, but the t's for the finite vowel group, they act by Q difference operators. So it's like some multiplicative analog of differentiation, like the de Bezrukavnikov. So we have that it's an algebra Hom, and now we need to show that it's a isomorphism.
How did you move from a theory of T star B to N to K? N is of T star G mod B.
Oh, sorry. Yeah, I forgot a tilde. Thank you.
Oh, okay.
Sorry.
Thank
Yeah, thank you. So now the next step is to introduce filtrations and show associated graded is an isomorphism. So this is like a very common approach to like showing things are isomorphism, like you have a filtered homomorphism. So there are standard filtration on both sides. On the left, you can take so the x lambdas or any polynomial on x, and then the t's are just bounded by w. And sort of it's immediate that the associated graded, well, this is just going to be a free rank 1 module for the polynomial algebra. Now, on the other side, the Steinberg variety itself, we can sort of, it has a decomposition by orbits, so by G orbits, and these are given by conormal to Bruja cell. Yeah. Silly thing where I use two different y's. Yeah, and this decomposition is like G cross C star stable. It's on the side. So now we can compute the K theory of both sides. It's again just going to be free rank 1 given by the structure sheaf of this conormal. Oh, I'll just write down. So the final thing before the break, the map theta, which was defined by generators, is filtration preserving. And on each sort of filtered piece, it's an isomorphism. So it just sends the T generator to some non-zero constant times the structure sheaf. So as a corollary of the theorem, theta is an isomorphism. Now we can take a 10-minute break. Pause. So now we need to do the categorical metric local Langlands. And I'll try to motivate it from ground up and avoid saying like as much as I can like scary words. Mostly due to my like understanding like or lack of. So let's just first recall the main thing we proved in the first half. So this is, I mean, the first complete proof of what I presented was in Chris Ginsburg, chapter 7. That was like the main reference. And the statement is that this Iwahori Hecke algebra is isomorphic to a theory of Steinberg, and it's on the sort of happening on the dual root system, and specialize that Q equals P. And I'm going to put this sort of as a comment. This is happening on the zero categorical level. Whatever that, just it's an isomorphism of algebras. Now, it was conjectured in Chris Ginsburg's book, I think that's the original conjecture, that there is a categorification of this isomorphism, namely one which first it's like independent of Q, you don't specialize Q, and furthermore, both sides here appear just as a equivalence of categories, so that when you take K theory of both sides, you get this isomorphism. And let me sort of build this up. First, on the left-hand side, we know by Grothendieck's function sheaf dictionary says, so we may replace functions on the double quotient by sheaves. I'll put on the affine flag variety. So this is going to be if fp bar p mod Iwahori. Then CG conjectures. There's some sort of equivalence between sheaves on the flag variety with sheaves on Steinberg. And this was proven by Bezrukavnikov. And this is sort of the first fundamental result on Affine Hecke Algebras. It's his paper called Two Geometric Realizations.
Why did we move from QP to FP bracket T?
I believe I could still write QP. I believe that if I replace QP here by FP bracket T, it's the same thing. Kevin, can I? No?
It's the-
So I don't know.
Okay.
One of the experts can help. The question is, why did we move from like p-adic to FP bar?
So this is supposed to be an easier version of the previous. Brackets T scheme over F. With QP over that. Yes. True. Okay, so do we expect a result also with QP? Just don't know how to define it. Like that's
I will say we're going to work with like this field of Laurent power series. And that's what the local here means. Like we just work over formal power series. Now, as mentioned earlier, we're going to consider the derived Steinberg stack. Then there exists an equivalence of categories between equivariant sheaves on the affine flag variety. Yeah, maybe I will write that, modify this over here as well. And the bounded derived category of coherent sheaves on Steinberg. So here, just concretely, this means we take equivariant complexes of L-adic sheaves. And since we sort of impose the coherence condition here, we have to also say with bounded and finite dimensional cohomology. And this is this accomplishes sort of the goal or the conjecture that Ginsburg made. So taking a theory of one recovers the isomorphism we stated earlier, and further specializing at P. Now, the goal of geometric local Langlands is to sort of run this, try to make a similar equivalence of categories where instead of working over FP bar everywhere, we work with the complex numbers. So in other words, it's the ROM setting. And I'll abbreviate this by GLLC, is to replace FP bar with C. And let me now formulate the conjecture.
So taking K theory of one, so when we in the usual dictionary between sheaves and functions, we use trace of forbidden, right?
Yes.
How is that related to taking? What is it now?
It's that comes at the next step.
Oh, okay.
Trace of forbidden is when you, I won't discuss it actually, but it's when you want to go between like C, complex numbers and FP bar.
Oh, I see.
Sort of, or formulate the two categorical version, and then trace of forbidden of that recovers to one categorical. So there's the conjecture due to gate scoring. There exists a Langlands functor which will be denoted by boldface L from category of modules of the loop group, taking modules of that. I'll explain everything shortly. To sheaves of categories of local systems on the puncture disk. And this functor is an equivalence of categories. Upon appropriate restrictions. I will not write them down. I'll only say them once. Here, there's a notion of equivalent singular support setting, and you have to use that. Now, let's explain what both sides really are. A reference for like this second half. So Gerbier has a very good exposition to categorical representation theory, where he explains this conjecture sort of at the end. It's written in a very like friendly expository way. Like even I could follow enough. Let's start from the beginning. So roughly, I'll explain what a DG category is. It's a collection of objects such that for each pair, the Helm spaces form a chain complex which are Z-graded. So that's what the DG stands for. And two, we have associativity of the composition. And a DG category is co-complete if it's closed under shifts, modes, and direct sums. Now the category of DG categories is denoted by DG cat. It's a one category whose objects are complete cats and morphisms are functors which commute with colimit. So this is the main definition. So the main fact is that DG cat is a unital symmetric monoidal under the Lurie tensor product. Excuse me. So example, well, vect is the unit object. So vect is like the each category of chains of vector spaces. The category of quasi-coherent sheaves on X is also the DG category. And the tensor product satisfies the property as you expect. And similarly, D modules. Category of D modules on X is a DG category. Now, since this category is monoidal, it makes sense to ask what are algebra objects for it. So an object of DG cat is an algebra, just a monoidal i.e. it has an associative multiplication. So, example, for any algebraic variety, we have the product map, and this induces by star push forward multiplication.
Or something.
Sure, yeah.
Said any algebraic variety. Okay.
Okay. Oh, all right, group. And we have algebras. Now it makes sense to ask for modules for these algebras. So given an algebra A, a module is such that the action map is associative. So a module for a DG category is a DG category itself, whose action map is associative. And here I'm sort of omitting many adjectives. Everywhere I should put parentheticals up to coherent homotopy, but I'm not going to write this down. So again, if Y is a G variety, we have an action map which under star push forward induces an action map. So we can decompose D mod on the product as the product of the D mod. So D modules on the variety are, write this down carefully. So they're modules for D mod G. Right, so D mod Y itself is a DG category, which is acted on by D mod G. And similarly, quasi-co is a module for quasi-co G. And just a non-example, just co is not. Like indico, quasi-co, those are algebras, but co is not. let me now define the loop group. So we have sort of unraveled what it means on the left-hand side, modulo of what the loop group means. So LG, it's a stack. To describe a stack, it just needs to specify what it does on test affine scheme. So we say for any C algebra, so everything's happening over C, the R points are just matrices with coefficients in Laurent series R of T. You can also define LG as a mapping stack from the punctured disk to the group. Okay, so D mod of LG mod sense. Really, okay, I explained D mod of something finite dimensional, like a finite dimensional group makes sense. Now D mod of LG, LG is an incoherent, or it's a in scheme, so we have to sort of really say, okay, this category of D modules is like the inverse limit of D mod of LG mod K, where K runs through all open compacts. Then, right, that's the definition, but it's minor point, and it's still symmetric monoidal, like because each one of those constituents to the limit is itself monoidal. Now we have to define the right-hand side. So what is a sheaf of categories? Well, okay, so let X be a space, any space in Lurie setting. So we only apply it for log sys. Then sheaves of categories on X is the association. So again, we define what it does to each test affine scheme. So for any affine scheme, we associate a module M inside the DG category of QCO S mod. So if X itself were affine, then the sheaf of categories on X is just QCO X mod. And even simpler, if X were just a point, then sheaf of categories of the point, well, this is just giving QCO of a point. This is just DG itself. So you just specify a DG category. So here, like DG categories, remember they are K linear DG categories, and QCO X means like it's OX linear DG categories. That's the difference. Okay, so now we have sort of made sense of both sides. Now we return to studying properties of the Langlands functor. So here it's this association cis check of the puncture disk. And now pretty much everything which follows will be a conjecture. And Kevin will tell us which one is a theorem. So first of all, the functor itself, it's given by Whittaker reduction. So here where n equals potent radical. So we take Whittaker reduction with respect to loops of n with this character psi. Yeah, I mean, we could have taken invariance or co-invariance. They're the same thing in this case. And here is actually what it does to many examples of D mod LGs, which we have encountered. So first is D mod on the affine Grassmannian. So this is G. So again, this is an object of D mod LG mod because D mod LG acts on this space on the left. And what Whittaker reduction does is maps it to quasi-co of point mod G check. And then this is rep G check by Castleman Shalaika. Okay, now what happens to D mod of loops G mod Iwahori? So this, called the affine flag variety, well, this will map to quasi-co of Springer on G check. Now, if we look at D mod of loops G mod loops N, psi. So like we Whittaker reduce loops G. This will map to quasi-co of Oxys G check of star. And finally, if we do D mod of BunG with sort of arbitrary ramification, so like the level structure is infinity, this will map to quasi-co of Loxis on the punctured curve. Okay, and now I can ask Kevin, are these all conjectural, or are any of them actually, or are they like
Doesn't exist.
on the functor doesn't exist? Okay, yeah, I remember you telling me. So this functor really, it's like we also have a forgetful map from sheaves of categories to DG cat. It's given by Obliv, and then Langlands composed with this forgetful functor is Whittaker. That's sort of the expectation, right? Okay. Okay, but modulo this expectation that these match up, you can actually deduce like everything. It's really cool. So it sort of patches together all of these Bezrukavnikov equivalences and more. Let's just give some applications. So assuming everything, like assuming equivalence of categories and these match up, we don't have isomorphism of objects themselves, but we have isomorphism of the harms between them. And to compute the harms of each object, we use the following sort of computation. Here's like a fact. So for any sort of, yeah, I'll just write it down directly. This is one fact, and similarly for B modules. So now when we compute harms between the left-hand side, we can greatly simplify things. So the first application will be just the Bezrukavnikov equivalence as formulated originally. And for that, we're just going to take endomorphisms of affine flag variety. So I'm suppressing a lot here. It really should say we take endomorphisms in the category D mod LG mod. I'll just write LG. Okay, so this, by this computation, this fact, we computed as D modules on what? We take loops G, okay, I'll just write it down directly. So here X is loops G mod. Oh, I meant to say Iwahori, sorry. So here X is loops G mod I, Y is loops G mod I, Z is loops G. So like it's just a exercise in fractions. You can cancel one of the loops G and you're left with just a single loops G in the numerator. I apologize, Kevin. And then on the Langlands dual side, so this is happening sort of on the automorphic side. This is on the Hecke algebra side. Now on the spectral side, has to, so where does it go to? Well, it goes to quasi-co of Springer mod G check. Then again, our fact says it's going to be, well, it's not going to be quasi-co, it'll be something slightly technical, but the same of what you expect. Check, cross, and tilde mod G check over G check mod. And everywhere, sort of, you can just think that this replaces local systems on the puncture disk. Okay. Let's now look at endomorphisms of the affine Grassmannian. And this now will be d mod of loops G mod positive loops G mod positive loops G. So L plus, maybe I can write it. I don't want to go too far up. L plus G is maps from the full disk. So then our points are just matrices with formal one power series with no poles. Okay. And I mean, what people like to call this space geometrically is the raviolo. So it looks sort of like you're gluing two disks along their puncture. So I don't know how to draw this best attempt. Okay, and then on the dual side, we compute endomorphisms of quasi-co of point mod G check. And again, this is going to be n co nope point times point over check. So in this sort of philosophy that Lie algebra G mod group G replaces local systems, I could have written point mod G times point mod G over G mod G. But there's G's everywhere. I can just replace pull it on the outside. And the equivalence on the right-hand side is very famous. It's called derived geometrics of Hecke. Steinberg will teach a full course on this next quarter. The third application is due to Arkhipov Bezrukavnikov. And this will be sort of the whole talk 3 and 6 discussing this. So here what you do is you take Palm from D mod on Whittaker D modules and D mod of affine flag variety. So again, we can just compute this using our fact that this is going to be D mod of loops G mod I on one side and mod Whittaker on the other. On the Langlands dual side, it will be quasi-co of local systems on the disk, quasi mod of LG I, n tilde mod G check. Okay, so this is now the HOM here is happening over local systems of D check. So it's like saying HOM from algebra, comma, like HOMs from algebra to this space, which are linear over this algebra. You can cancel this out. So this is just quasi-co of n tilde mod G check. That's precisely what the AB equivalence is. Now the ABG so this will be log 4. This is going to be modding by EOHOR on one side and by positive loops on the other side. So Sorry, I wrote down the same thing. And I'll just write down the answer. This is just going to be quasi-co of point times and tilde over check. And maybe just the very last thing I'll say is you can also fit in the global unramified geometric Langlands, which was just proven. This framework. Here, what you do is take from the mod of G, the mod of BunG with infinite level structure. So then what this will be, well, if you do loops G, mod positive loops G, and then BunG infinity X is like modding out by G out. So this by uniformization theorem is exactly BunG. So that is one side. And now on the Langlands dual side, what we have is quasi-co of local systems of G check on the disk times local systems on the punctured curve over local systems of the punctured disk. And this is precisely just quasi-co of local systems of the curve. And yes, this is like the, without any decorations. This is exactly the statement of geometric Langlands. Okay, I'll stop here.
Supposed to be not exactly quasi-co and some fixing.
Yes, there should be a potent singular
Okay.
support. Yeah, like that, taking here, if you take endomorphisms in the correct category, you'll get that corrected.
Oh, I see. That's
Yeah, adjectives. Any other questions?
yeah. Yeah.